This is the idea, right? So we know about parametric curves, we know about scalar fields that can assign a scalar to every point in space, and what you're doing is you're traveling along the parametric curve, and along your path you're adding up all the little values of the scalar field, the way that an integral adds things up. So now we have a formula for calculating a path integral over a scalar field, and this little bit of notation is saying, listen, I'm taking an integral over this path and over this scalar field. And it looks exactly like taking the length of a parametric curve, but instead of just adding up these little length segments, we're multiplying the length of the segment times the value of the scalar field. So you throw in a little f in the integrand and boom, path integral. This is a lowercase gamma. If you've never seen that before. It's a lowercase Greek letter gamma. And that is my preferred notation that we use when we talk about parametric curves in the context of path integrals. That's what I'm used to. Questions so far? No? Okay. The other thing that we're learning today is a path integral over a vector field. So if I want to indicate to you that I'm taking a path integral over a vector field, I'm going to use the capital letter F to indicate that's a vector field, and then the lowercase gamma tells me what path I'm integrating over. And the difference here is that we are going to take the dot product between my vector field and my derivative of the parametric curve. So it's like the velocity of the parametric curve. It's telling me what direction I'm moving in. And so the dot product between the vector field and the velocity, right, is kind of telling me how aligned is my path with the direction of the vector field. If the vector field direction is pointing exactly the same direction as my velocity vector, then this integrand is going to have its maximum value. If these are orthogonal to each other, like if you're traveling orthogonal to the direction of the vector field at a 90-degree angle, then the integrand is going to be 0, regardless of how strong the vector field is and regardless of how quickly you're moving in that direction. If the vector field is pointing in the opposite direction of your velocity vector, so you're moving opposite the vector field, you're going to have the maximum value but with a negative sign. So in terms of fish, like salmon are swimming upstream, they're swimming against the vector field, they're going to have a negative integrand in their path integral because you're going velocity against the vector field. And so whenever I take this dot product, right, you're just multiplying the first entry of the vector field times dx dt and so on. You know how to take a dot product. Questions about that formula? These are things you got to memorize before our next test. And again, hopefully it's not that bad for memorizing because you've already memorized the length of a parametric curve. And all we're doing is adding the scalar field or multiplying by the scalar field in the integrand. And again, you really must memorize the vector field thing, but all you're doing is taking the dot product between your vector field and the derivative of your parametric curve. So here's an example. Find the total mass of the wire with shape gamma and density rho. So this is going to be an integral over the scalar field rho over the path gamma. So in other words, it's going to be an integral from a to b of rho times the norm of gamma prime. So this would be an integral from 0 to 4 pi of x squared plus y squared minus 3z times the square root of not gamma, but the derivative of gamma. Maybe I should just go ahead and write this out. Take it one step at a time so I don't have to make any mistakes. The derivative of cosine is negative sine. The derivative of sine is cosine, and the derivative of t is 1. And so that's going to be negative sine squared plus cosine squared plus 1 dt, which is the integral from 0 to 4 pi. And what's sine squared plus cosine squared? 1. It's really like the square root of 2. And the next thing we're probably wondering about is like, what do I do with x squared and y squared and z if I'm taking the antiderivative with respect to t? Well, x and y and t are functions of t. We just have to tell my integral what those functions are. Like x is negative sine of t, and y is cosine of t. And, oh, sorry, that's wrong. My bad. Let me fix that. X is cosine of t, and y is sine of t, and z is t. So whenever I have the x, I'm going to replace that with cosine t. When I have the y, I'm going to replace that with sine of t. When I have z, replace that with t. So when you come to the point where you need to replace x, y, and z with t's and your integral, you're going to use the original parametric curve equation, not the derivative, but the original. And then, of course, cosine squared plus sine squared is 1. So this is going to be 1 minus 3t dt, which is going to be t minus 3 halves t squared. We can plug in the 4, and we're going to get 4 minus 3 halves times 16, which is 4 minus 3 times 8, which is 4 minus 24, which is going to be, ooh, I was saying 4 too much. I almost wrote down the wrong thing. Negative 20 square root 2. Where'd the pi go? Good catch. Oh no, it's not that easy. I've got to think about that a little harder. So it's 4 pi minus 24 pi squared. And that's it. I should really fix this problem so we don't have a negative mass for my spring. I think before next year I'm going to make it so that the density is positive. You know what I'm saying? Because making this a negative 3z is giving me a negative density. And I don't want to have a negative overall mass to my spring, but oh well. That's why it's a math class and not a physics class. By the way, any questions about this? No. All right, so you remember from physics that work is force times distance. But specifically, when we say force times distance, we're saying that the work is done only if the force is in the same direction as the distance. And if it's not, if like your force is in this direction, your distance is moving in this direction, you're going to take the dot product so that you only get the component of the force that's acting in the direction of the distance. So it makes these path integrals over vector fields super useful in the case where your force is varying in both direction or magnitude or one or the other, and you're traveling some distance across a path that may or may not be a straight linear path. Like, find the total work done by the force field F on an object passing through the field along the path gamma. So we are taking a path integral over a vector field. And that means we'll take the integral from a to b of my vector field dot product with the derivative of my path with respect to t dt. So I need the derivative. We already found the derivative earlier. It was negative sine cosine 1. So it's the same curve from the previous exercise. We're just reusing it now with a vector field. And this will be 0 to 4 pi. And when I do this dot product, I'm thinking about the first entry in the vector field times the first entry in the derivative of the parametric curve plus the second entry in the vector field times the second entry in the derivative of my parametric curve plus the third entry in the vector field times the third entry in the derivative of my parametric curve, so that's z times 1. So far, so good. And now I'm going to replace x and y and z with cosine, sine, and t from here. So instead of x squared, I'm going to write cosine squared. Instead of y to the negative 1 power, we are going to write sine of t to the negative 1 power. And instead of z, I'm going to write t.
You dropped the pie again.
Man, I just hate pie today.
It's gonna be ice cream instead.
That's right. Not a pie guy. So we've got cosine squared over sine and a negative cosine squared over sine.
Why is it over sine?
Oh, sorry. I don't know why I wrote that over sine. I think I'm thinking about this -1 power, but clearly I'm in the wrong spot for that. So it's cosine squared times sine. That's actually easy to solve with a u substitution, isn't it? This one is cosine divided by sine. Which is also easy to solve with a u substitution, isn't it? And then this is t. I like that. Because u sub is not that bad. What do I do for u sub in this case? Cosine, right? I mean, tell me if I'm wrong. Could it be negative sine dt? So this becomes u squared du. The lower bound is cosine of 0. Upper bound is cosine of 4 pi. So that's actually just 0, isn't it? An integral from 1 to 1. Okay, moving on. The middle, what's my u sub? What? When you student teach, do kids do that to you? Do they sit there the whole time and make hand gestures and...
What?
You're right. Never mind.
When he was talking about orthogonal,
Well, I'm trying to picture it. Looking at your finger.
What's my u sub for cosine over sine?
U sine.
Sine. And then du would be cosine of t dt. So this is the integral of 1 over u du. The lower bound is sine of 0, and the upper bound is sine of 4 pi. Oh, wow. That's crazy. What is the last one? I'm going to get 1/2 t squared, which is 1/2 4 pi squared, which is going to be 16 divided by 2 pi squared. So if I have some force field that's described by this, maybe it's a gravitational field, maybe it's the electromagnetic force, I don't know. I'm not a physics person. But then you have some object or particle moving through the force field according to some path. Well, you could calculate the work done by the force field on the object. using a path integral over the vector field over the parametric curve, over the path. Questions about that? Okay. This is called the fundamental theorem of calculus for path integrals. In Calc 1, you learned the fundamental theorem of calculus. Do you remember what the fundamental theorem of calculus says? It says this. And in the Calc 1 world, you've got just like a single variable function f. Well, if you take the antiderivative of your integrand, and then you plug in the upper bound and the lower bound, and you subtract the two, that's called the fundamental theorem of calculus. Because in Calculus 1, what you're supposed to do is you're supposed to define the integral of a single valued function as like the Riemann sum, the limit, and the Riemann sum as n goes to infinity. And in Calculus 1, then you, I don't know, hopefully maybe just saw your professor prove the fundamental theorem of calculus that connects the antiderivative to the Riemann sum limit. But anyways, that's what's normally called the fundamental theorem of calculus. This is not just the Calculus 1 fundamental theorem of calculus, but this is now the fundamental theorem of calculus for path integrals. And it says, suppose you've got a conservative vector field, and lowercase f is the potential field of your vector field capital F. Then for any path gamma whose parameter starts at A and ends at B, a path integral over the conservative vector field is going to be equal to the potential field evaluated at the end point of the path minus the potential field evaluated at the start point of your path. Which means that conservative kind of has like physical interpretation. You know, if you were to take a path from the top of Mount Everest to the bottom of Mount Everest, your gravitational potential energy changes. You have more gravitational potential at the top of the mountain and less gravitational potential at the bottom of the mountain. And the change in potential wouldn't matter, it wouldn't depend on what path you take down. You can go down the north face, the south face, the east face. It doesn't matter how you hike down the mountain. You still get the same change in gravitational potential. It turns out the gravitational field is a conservative vector field. It's a vector field because it acts in a particular direction. And there is a potential field because we can talk about gravitational potential energy. So a proof of why this has to be true is you could say, since capital F is conservative, the potential field exists and capital F is the gradient of lowercase f. Those are just definitions that we learned in previous lectures. Now, taking the path integral over capital F would be like taking the path integral of the gradient of lowercase f and a path integral over a vector field is the integral from A to B of the vector field dot product with the derivative of the path. And so the derivative of the path is going to be expressed like this: dx dt, dy dt, dz dt. And when I take the dot product, this is going to be the derivative of f with respect to x times the derivative of x with respect to t, plus the derivative of f with respect to y, times the derivative of y with respect to t, plus the derivative of f with respect to z, plus the derivative of z with respect to t. And I know I've made a little tiny mistake here, that I should be using partial derivatives for the f part. That should technically be the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. Because the gradient is actually the partial derivatives. Oh, sorry, that's not right. That's not the gradient. Those are real derivatives. Okay, it's all right in the end. There we go. So what is the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt plus the partial of f with respect to z times dz dt? This is what you would call the total derivative of f with respect to t. And if I'm taking the antiderivative of the derivative of my potential field, then it's really the potential field evaluated at the end point minus the potential field evaluated at the start point. And at some point along here, we're to switch the bounds. Oh, that plus sign doesn't belong. But at some point along here, you switch the bounds from being like from A to B to gammas. Maybe I skipped a step. Let me insert a little step in here. Yeah. Kind of lost the plot a little bit. Not 100% sure when these switched from being just A's and B's to gammas of A's and gammas of B's.
Well, how did it change from gamma to A to B in the beginning?
Well, that's like part of the whole definition here of what we mean when we say we're going to take a path integral. Right, so if I were to write this, it's just kind of like shorthand. It tells you all you need to know. It tells you what your integral is, what vector field you're integrating over, and what path you're integrating over. What it kind of represents is saying, like, I'm adding up all of the little chunks of vector field times the little chunk of path that I'm taking, the d gamma. And then, you know, what are we actually, how do we actually calculate that? That's when we multiply by like dt over dt, if you will. Because it's not obvious what you do to calculate with. This is something we can calculate. This is just some kind of conceptual idea that we're going to take the value of the vector field at every point and multiply by a little chunk of path. And that path would have a direction, right? It's not like in the scalar field sense when the path we only care about the length of the path segment, but this is actually talking about the length of the segment and its direction. Because we care about how much it aligns with the vector field. So maybe I can't remember off the top of my head what the right notation is for writing this step here. But as long as there's a dt at the end, I guess it should be an integral from a to b. The problem is like, where do the gammas come up again? And maybe the right answer is like, I don't know. I don't know. There should be like a little d gamma here. So that way we can switch the bounds to gammas. But it's another one of those little mysteries. Maybe we'll talk about this again next class. So, more definitions, more theorems. A path is closed if the start point and the end point are exactly the same. Closed means the start point and end point are the same. And the proof of this theorem saying, okay, I want to integrate a conservative vector field over a closed path, that's going to give me a 0. The proof relies on that fundamental theorem of calculus for path integrals, because we know now that if I were to take, let me scroll up so I don't forget this, I don't write it down wrong. The path integral of a conservative vector field, it would be equal to the potential field at the end point minus the potential field at the start point. And if we're saying this is a closed path so that the end point is the start point, well, then this is the same thing, right? So what does that mean? If you've got a conservative vector field, like the gravitational field, you start at the base of the mountain and you make a closed path, like you hike up the mountain, you hike down the mountain, and you hike around the mountain back to where you started from, then your potential is the same. There's no change in your potential. Your potential at the end is the same as the potential at the start, because your start location is the same as your end location. And that means if you were going to take this integral, then the integral should be equal to 0. Okay. So we'll see how far we can go, because we started at 12:15, so we actually have until 1:30. This is still a lot of time left. This exercise says, show that the following vector field is conservative. Show that gamma 1 and gamma 2 start and end at the same point, and then take the path integral over gamma 1. So do you remember, how do we show that the following vector field is conservative?
Is it with the curl? Is curl 0?
Yeah. Curl 0 implies that this is conservative. So what we should do is we need to take the curl of f And the curl of f is like the cross product between the gradient operator and my vector field. And I have to make a little note for myself for what the cross product formula is. It's uv minus uv. Two, three, 1, 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. So the gradient, of course, is the partial with respect to x, the partial with respect to y, the partial with respect to z. And so that means u2 is the second entry in the gradient, which means it's the partial with respect to y. v3 is the third entry in my vector field, which is xy, minus the partial with respect to z of xz. Then my next entry is going to be the partial with respect to z of yz minus the partial with respect to x of xy. And then the last one's going to be the partial with respect to x of xz minus the partial with respect to y of yz. So it's going to be x minus x, y minus y, z minus z. So it is irrotational, because the curl is 0, and conservative. Because if a vector field is irrotational, then a vector field is conservative. So that's how you do bullet point number 1. If I ask you to show that a vector field is conservative, that's how you do it. Bullet point number 2 says, show that gamma 1 and gamma 2 start and end at the same point. So I've got A1 as 0, B1 is 3. So if I take gamma 1 at A1, that's 0, negative 4 times 0, 0 squared. And here I have A2 and B2. If I take gamma 2 at A2, that's 0 squared, negative 4/3 times 0 to the 4th, and 0 to the 4th. And these are both the point 0, 0, 0. Next, if I take gamma 1 at B1, the end point, I'm plugging in the 3, so this is going to be 3, negative 4 times 3, and 3 squared. If I take gamma 2 at B2, this is going to be the square root of 3 squared, negative 4/3 times the square root of 3 to the 4th power, and the square root of 3 to the 4th power. And both of these are equal to what point? So we just did bullet point number 2, where it says, show that gamma 1 and gamma 2 start and end at the same point. Their parameters don't have the same end point, but whenever I plug in those endpoints for the parameters into the correct parametric curve, I find that they both start at the point 0, 0, 0, and they both end at the point 3, negative 12, 9. The next thing I want to do is take the path integral over gamma 1. So let's integrate that vector field capital F over the gamma 1 path. And so I've got the integral from 0 to 3 of f dot product with the derivative of gamma and the derivative of gamma 1 with respect to t is going to be the vector 1, -4, 2t. So when I take the dot product, it's going to be 1yz plus -4xz plus 2t xy. All right, now I've got this antiderivative with respect to t, this integral with respect to t. What do I do with all the x's and y's and z's? Replace them with what? T, -4t, and t squared. So I'm replacing the y with -4t and the z with t squared. This is going to be -4t cubed minus 4 times t squared plus 2t times t times -4t. So it's like minus 8 t cubed dt. So altogether, it's going to be -16 t cubed dt. I take the antiderivative, and so it's going to be t to the 4th, and so it would be -4 t to the 4th power. And I plug in the 3. 3 to the 4th power is 81. And so it's a big number. I think. Questions? So let's do the second half of exercise 8, if there's no questions. The second half says take the path integral over gamma 2. Here's gamma 2. So now we've got to do the same path. No, not the same path, a different path, same vector field. And that'll be the dot product between f and the derivative of gamma 2 with respect to t, which is going to be the vector 2t -16/3 t cubed and 4t cubed. So in the dot product, I've got yz times 2t plus xz times -16/3 t cubed plus xy times 4t cubed. And then, of course, I got to replace all the x and y's and z's. And the y is going to be negative 4/3 t to the 4th. The z is going to be t to the 4th. So that's altogether t to the 9th power. And 2 times negative 4/3 is going to be negative 8/3. Plus negative 16/3 times x times z, which is t to the 6th times t cubed is t to the 9th. And then 4 times t cubed times x times y is t squared, t to the 4th. It's also going to be t to the 9th. Negative 4/3 times 4 is negative 16/3 again. dt. So that's negative 40/3 times t to the 10th power divided by 10 evaluated at square root of 3. Or negative 4/3 times the square root of 3 to the 10th power, which is negative 4/3 times 3 to the 5th power, which is negative 4 times 3 to the 4th power, which is negative 4 times 81, which is negative 324. Haha. So I'm glad I didn't make any mistakes because we got the same answer. One way was easier, I think. I think the first time we did it was slightly easier to get that way. But the point is, it doesn't matter whether you take the path gamma 1 or the path gamma 2. And they're legitimately different paths that have a different shape going through space. But regardless of which path you were to take from one point to the next, you get the same integral because this integral is path independent. It's a conservative vector field, and path integrals over conservative vector fields are path independent. Find the potential field. So we know how to find potential fields after last class. The next bullet point says find the potential. And here we go. Since I know that the gradient of my potential field is this vector field f, that means I should be able to take this yz and take the antiderivative with respect to x and get back my potential field. And I should be able to take my xz and take the antiderivative with respect to y and get back my potential field. And then the last entry is xy, and if I take the antiderivative with respect to z, I should be able to get back my potential field. So what is the antiderivative of yz with respect to x? xyz. What's the antiderivative of xz with respect to y? xyz. What's the antiderivative of xy with respect to z? xyz. And so this doesn't always work out exactly like this. You know that sometimes you get different terms and different antiderivatives, and you've got to totally combine them. Not necessarily add them up, but look for the ones that are missing from one another. But in this case, it was really easy. My potential field is going to be this: x times y times z, plus a constant if you want. And then the last thing says verify the fundamental theorem of calculus for path integrals applies to this vector field. And of course it does, right? Because it's a conservative vector field. But what the last bullet point is wanting me to do is say, we know the fundamental theorem of calculus for conservative vector fields, path integrals, is this. So what I want you to do is look at the start points and the end points. The start point, remember, was 0, 0, 0. And the end point was 3, negative 12, 9. And so those are going to be my start point and end point. Oops. And so the potential field is x times y times z. So in other words, it's going to be 3 times negative 12 times 9 plus a constant minus 0 times 0 times 0 plus a constant is going to be 3 times negative 12 times 9, which is negative 324. So exercise 8 is kind of making you do extra work that, you don't really have to do, because you know based on the theorem that this was a conservative vector field that's going to be path independent. But the point of exercise 8 is to show your work and show me that you can do the work to calculate the path integral along the first path there in plum or magenta or whatever you want to call that color. And then you can do the work to take the path integral over the second path there in green, and that you can even do the fundamental theorem of calculus for line integrals, and you still get exactly the same answer, right? Negative 324, because it's path independent. Evaluate the following path integral. So you got a vector field. We're taking the path integral over the vector field. And gamma is the path through the xy plane from 0, 0 to 4, 4 shown below. You guys got that? So if you see something like this on a test, this is hopefully a clue that this is going to be path independent, right? You're not supposed to sit down and figure out a parametric curve that goes through all those points. What you're supposed to do is think, is f conservative? I hope so. And then we take the curl of f to demonstrate that this is going to be conservative. And that's the partial with respect to y of negative 4y plus 20z minus the partial with respect to z of negative 4z. The second entry in my curl is going to be the partial with respect to z of 6x minus the partial with respect to x of negative 4y plus 20z. And then the third entry in my curl is going to be the partial with respect to x of negative 4z minus the partial with respect to y of 6x. So the curl of f is negative 4 minus negative 4, 0 minus 0, 0 minus 0. And so yes, it is conservative. You know, in some sense, most vector fields are not conservative, because if you even make like a small perturbation to any of those entries in one variable only, then you'd come up with a vector field that was not conservative. But it's, I guess, a happy accident that in physics almost all of the vector fields that you deal with are conservative vector fields. So we deal with a lot of conservative ones in this class because it's an important idea. So since this is a conservative vector field, its integral is going to be path independent. And that means I'm going to be able to solve this integral by taking the potential field at the end point and then subtracting the potential field at the start point. So we just have to find the potential field. And to find the potential field, I'm going to rewrite the vector field down here, 6x, negative 4z, and negative 4y plus 20z. And I'm going to take the antiderivative with respect to x, and the antiderivative with respect to y, and the antiderivative with respect to z. And I should be able to recreate my potential field. What's the antiderivative of 6x with respect to x? 3x squared. What's the antiderivative of negative 4z with respect to y? Negative 4yz. What's the antiderivative of negative 4y plus 20z with respect to z?
Negative 4yz plus 10z squared.
Perfect. And remember, these constants aren't necessarily constant. It's just that this constant is constant with respect to x, but it could be a function of y and z. And this constant is really just a constant with respect to y, but it could be a function of x and z. And this constant is really just a constant with respect to z, but it could be a function of x and y. So whenever I go to put together my potential field, I'm going to write down 3x squared minus 4yz plus 10z squared plus a genuine constant that's just a constant number. Now I just need to plug in the values of x and y and z at the start point and at the end point. I'm starting at 0, 0 and ending at 4, 4. So when I start at 0, 0 and end at 4, 4, I'm going to subtract these. So if I plug in 4 for x and 4 for y, this is going to be 3 times 16, and z is 0, right? Minus everything's 0 when I plug in 0. So it'll be 48.